Can you hear me? Hello? Fang Kang? Oh man.
Okay.
I thought you left without me.
Because you said that we can come together.
Okay, this number here, okay? You just talk into this number, and then if you need the password,
Okay. Wow.
halfway you will take a break, okay? 10 minutes.
Okay, okay. Okay, wait for. Oh, it's okay.
Yeah.
I just wanted to let you know what I have included.
You have discrete convolution also, I saw. I think that's
Yes.
easier. Yeah.
Yes, that's easy. Wait for a while. I need to connect that to. Okay, okay.
And don't go down.
Okay, okay.
Yeah, you can ask these people whether they can hear.
Can people on the Zoom hear me? Can everyone hear me? You can type yes. Okay, I assume that you can hear me. Okay. So let's start. So today we are going to continue to finish the section 4.1, the derived distributions. So in this section, we are going to talk about two parts. The first part is the functions of two random variables. And the second part is the sum of two random variables. So first, let's begin with the functions of two random variables. Let's first recall the two-step approach when we derived the PDF for a function of y equal to gx. So in the previous lecture, we have learned how to derive the PDF of y equal to gx. So first, we obtain the CDF of y using this probability of gx smaller than y. And then we differentiate this CDF function to obtain the PDF function. Okay, so this is what we have included in the last lecture. And this two-step approach can also apply to this function z equal to g of x and y. So this is a function of two random variables instead of just one random variable. So let's just start with an example to see how we can apply the two-step approach to derive the PDF of z. So suppose we have an archer who shoots a target 2 times. And the distance of each shot to the center is uniformly distributed. On 0 to 1. And here it's naturally to assume that each shot is independent of each other. So let's say x to be the distance of the first shot. the distance of the second shot. So now we see that x, and y are two independent random variables. So it represents the distance of the shots to the center. So we want to know the PDF of the distance of the worst shot. So the worst shot means that the shot has longer distance. So we define a random variable z to be the distance of the worst shot. So z is equal to the maximum of x and y. So z is either x or y. It takes the maximum value. So now we have the function of z here, function of x and y, which is equal to z here. And then we can apply this two-step approach. So for the first step, we derive the CDF of z first. So for any z, this is small z, the CDF of z equal to z is the probability of max x and y smaller than this z. So we want to simplify this probability. So we can notice that the events max x, y smaller than z, this event is equivalent to events x smaller than z and y smaller than z. So these two events are equivalent. So we have that the probability of max x, y smaller than z can be rewritten as x smaller than z and y smaller than z. And since we already know that x and y are independent, so we can split this probability into the multiplication of the probability of y smaller than z times the probability of x smaller than z. So this from the because x and y are independent. So the next problem to be solved is the probability of x smaller than z and the probability of y smaller than z. First, let's plot the PDF of x and y. So we know that x and y are uniform over 0 to 1. Then the PDF can be plotted as this. This is x, this is fx. And between 0 to 1, this is and this is also equal to the PDF of fy. So according to this plot, we can see that x and y only takes value from 0 to 1. So it's natural for us to split the different values of z according to smaller than 0, from 0 to 1, and for z greater than 1. So we want to split the different values of z into 3 cases. first, we want to for any z smaller than 0, then the probability of x smaller than z can be calculated by the integration. Okay. So since we can see for when z is smaller than 0, the PDF is equal to 0. So the integration must be 0. And then for the second case, when z is in between 0 and 1, we use the integration to calculate the probability. So now, since z is here, somewhere here, and then we can write this integration into this summation. First, we integrate from -infinity to 0, and then we integrate from 0 to z. So this, since the first term is equal to 0, since the fx is equal to 0. And then the second term is simply z. So this is, so when z is in between 0 and 1, the probability of x smaller than z is equal to z. And then we have the third case for any z greater than 1. Still the same, we calculate the probability of x smaller than z. So this time z will be somewhere here. So we can see that this horizontal line can be split into 3 parts. So if z is somewhere here, then we do the integration as follows. First, we integrate from -infinity to 0. And then we integrate from 0 to 1. Finally, we integrate from 1 to z. So the first term is equal to 0, and the second term is exactly 1, and the third term is still 0. So finally, we have that the probability of x smaller than z is equal to 1 when z is greater than 1. So now we obtain the probability of x smaller than z for any values of z. And similarly, since y and x has the same distribution, so the probability of y smaller than z is the same. Z is smaller than 0 is equal to z when z is in between 0 and 1. It's equal to 1 if z is greater than 1. So for now, we already obtained these 2 probability. And then we can just plug in inside and we obtain the CDF of z. So by plugging this result inside, smaller than 0, then fz is equal to 0. If z is in between 0 and 1, then it's the z square. If z is greater than 1, then the CDF is equal to 1. So for this case, So for this example, for now, we obtain the CDF of Fz. And next, to obtain the PDF of Z, we just need to do the differentiation to the CDF. So in step 2, to obtain the PDF, we just do the differentiation for different values of Z. First, when Z is smaller than 0, then the PDF is equal to 0, since the CDF is a constant number 0. And when Z is in between 0 and 1, the PDF of Z will be the differentiation of the Z square over Z, which is 2Z. Greater than 1, it's still 0 since the CDF is a constant number 1, so the differentiation over Z is still 0. So in summary, Z is equal to 2Z if Z is in between 0 and 1. And is equal to 0 otherwise. Okay, so this is a very simple example that shows how we can apply the two-step approach to the functions of two random variables. Then we move on to the next example, which is a bit more complicated. So first, we assume that X and Y are two independent random variables, uniform. From 0 to 1. So this is a simple assumption for the X and Y. And now we want to consider this function is equal to Y over X. Okay. So first we notice that since X and Y only takes value in between 0 and 1, and we want to discuss different values of Z, so it's natural for us to split into 3 cases. Consider 3 separations. Z smaller than 0, Z in between 0 and 1, and Z greater than 0. So when we want to calculate the CDF of Z, we still need to split the different values of Z into different cases. So for step 1, we want to derive the CDF of Z. First, when Z is smaller than 0, CDF is equal to the probability of Y over X smaller than Z. And since we already know that X and Y takes value in between 0 and 1, so we can multiply X on both sides. So this is equal to the probability of Y smaller than XZ. And how can we calculate this probability? So an easy way is to still plot the figure So this time, we don't plot the figure of the PDF of X or Y. Instead, we let the horizontal axis to be X and the vertical axis to be Y. So now we have a region of X and Y. And 0, 1. So we know that X and Y only takes value in between this, inside this rectangle, because it's uniformly distributed on 0 to 1. And each point in this rectangle has the same distribution. So they are all uniformly distributed. Okay. So let's first use the red color. So let's first plot a line of Y. Oh. Y equal to Zx when Z is smaller than 0. So this is a line that looks like this. Okay. So this is the line of Y equal to Zx. And then so for the area under this line, it represents the Y is smaller than Zx. Okay. However, since Y only takes value in between 0 to 1, so this case is impossible. Thus, this probability is equal to 0. Does it make sense? Because Y is only uniformly distributed in between 0 and 1. So it only appears here. Yeah. Then for the second case, so when Z is greater than 0 but smaller than 1. The CDF of Z is still equal to the probability of Y smaller than XZ. And then this time we plot another line. This is Y equal to ZX, but Z is in between 0 and 1. So this line must be the green line must be lower than the blue dotted line because Z is smaller than 1, but greater than 0. And then for the area, but so the area, the triangle under this line represents the area where Y is smaller than ZX. Okay. So the probability of Y smaller than XZ is equal to the area of the triangle over the whole area of this rectangle. So this area, first we need to know the value of this point. This is equal to Z, this point. So this triangle is equal to, the area of the triangle is equal to Z over 2, and the area of this rectangle is equal to 1. So this probability is exactly equal to Z over 2. For the third case, when Z is greater than 1, CDF of Z is still equal to the probability of Y smaller than XZ. So for this time, we plot another line. This is equal to Y equal to ZX for Z greater than 1. Okay? And then this point corresponds to the X equal to 1 over Z. So this time, for the area when Y is smaller than ZX, is this purple area. Okay. This is smaller than ZX. So the probability, so this probability will be equal to the area, purple area, so this purple area is equal to 1 minus the area of this triangle. So this triangle is equal to 1 over 2Z. Now we obtain the CDF of Z for different cases of Z. I can't hear you. Oh, okay. So we see that this point, the Y is equal to 1 for this point, and Z is equal to 1 over Z. So the area of this rectangle will be 1 over 2Z. So the whole area, so this purple area will be 1 minus 1 over 2Z. So for now, we can just differentiate the CDF of Z to obtain the PDF, which is very easy. So if Z is smaller than 0, then the differentiation is just 0. Z is in between 0 and 1. So we take the differentiation over Z over 2, which is equal to 1 over 2. Z is greater than 1, the differentiation of 1 minus 1 over 2z, this is equal to 1 over 2z squared. So now we obtain the PDF of z finally. Is there any problem on the Zoom? Any other problem? If you have any question, you can just ask me. Of course, you can do it with respect to the y, but see, so then the probability would become x greater than y over z. Oh, no. So for z, because z can be positive, can be negative. So if z is negative here, then this probability will be written as z greater than x. And then you can use the similar method to calculate this probability. You can just use this plot. To make it clear, we can write it in the following. So I write it here. So if z is smaller than 0, then fz, the CDF of z, can be written as y over z greater than x. Z in between 0 and 1, then this is equal to y over z smaller than x greater than 1. So we can just use this rectangle area and we plot the line of x equal to y over z, and then do the similar analysis. But I think that for this kind of analysis is more complicated than using just this probability. So we prefer using this form. Any question on the Zoom? So let's move on to the second part. So let's move on to the second part, which is a special case of the functions of two random variables. That is the sum of two independent random variables. Assume that x and y are two independent random variables. So let's Z to be x plus y. So when we calculate this PDF of Z, we will use something called convolution. So later we will know what is convolution. So first, let us consider the simple case when x and y are just integer valued random variable. Assume they are just integer valued, so that they only have PMFs. Px and Py. So PMF of Z is given by the following. So for any integer, the PMF of Z taken value at Z is equal to the probability of Z equal to Z. And this is equal to the probability of x plus y equal to Z. So we know that x and y can take up different values, but their sum is equal to Z. So x, y can take sum is Z. So that we have this. So the probability of x equal to x and y equal to zx. So in this event, x takes up value x and x plus y is still equal to z. So x can be any values. So we need to sum over all the possible values of integer x. So here, x is integer. This probability can be written into this form. Since x and y are two independent random variables, so their joint PMF is equal to the product of x times the probability of y equal to z minus x. So this is because of the independence. X and y are independent. we can represent it using the PMF of X and the PMF of Y. Now the PMF of Z can be represented using the PMF of X and Y together, which looks, this form is what we call the convolution of PMFs of X and Y. This Z is fixed. We are summing over all the possible values of X. Give an example. Say that Z is equal to 3. And then consider at the value of 3. So first, let's plot a figure. The horizontal axis is X and the vertical axis is Y. Since they are discrete values, that is, they are integer values, so they can only take value from at -1, 0, 1, 2, 3, 4, and so on. Okay, so same for Y. So that when X plus Y is equal to 3, it means that we are taking this point, there are so many points outside. So all these points are pairs of X and Y such that X plus Y is equal to 3. Y equal to 3. Then of Z at 3 is equal to the probability of X plus Y equal to 3, which means it's equal to the sum of all the probabilities of these points, this pair of points. It's just the probability of X equal to X and Y equal to 3 minus X. So these are the pair of points of the red points. Right? So this is so still from the independence of X and Y, this is equal to the product of these two probabilities. And that is the PMF of X at X and PMF of Y at 3 minus X. So this is the sum of the probabilities. All pairs of Y So this figure can help us better understand how we go from this step to this step. So let's have a break here, and then we can come back in 10 minutes. From where?
Sorry, is it like the PY greater or equal to?
This is the which? This is the first example, is
Yes,
it? Oh, I see. So, oh, it's okay. So let's see. So first
After you derive
So first we derive the probability of X smaller than Z and probability of Y smaller than Z.
Yeah.
So, and this FC is equal to the product of them.
Okay. Ah.
Yeah.
Okay.
So you just times.
Just times them together.
Yeah.
Okay.
Yeah.
So this is only doing for the Y. So after you do for X, then you just add them up.
Yeah,
them together.
because X and Y have the same distribution.
Okay.
So their probability is the same. Yeah.
Okay, I understand.
Yeah. No problem. Continuous random variable for the continuous.
Do you have an example for discrete convolution?
This is so.
The three. This one.
This one is already the
okay.
discrete
So you
one.
only have to talk about the continuous convolution.
Yes, yes.
And the box example.
Oh yeah, yes.
Uniform.
I just use one example to.
Okay, so you just have the continuous left. Okay.
Oh yes.
I think you should be okay in time.
Okay, I think it should be okay.
We start around
57. Because
57 is okay. Yeah.
Okay, because I need to talk all this.
Oh my gosh.
It's very it takes some time, I think.
I don't know whether people learn this before or not, because usually in signals and systems they will learn it before.
Oh yes, yes. Yes. Okay, sure. Okay, let's start. Everyone on the Zoom, we are going to start. So just now we finished discussing the discrete case when x and y are integer valued random variables. So for now, we are going to continue to the continuous random variables. So let x and y be independent, continuous PDFs. Okay. So first, we consider this conditional probability first. The conditional probability of z equal to z smaller than z when x is equal to x. This is equal to the probability of x plus y smaller than z given x equal to x. So since we already know that x is equal to x, so we can just replace this x here. This is equal to the probability of small x plus y smaller than z. Even is equal to x. Okay. So divide it to the better form, which is y smaller than z minus x given x equal to x. So since y and x are independent, so this conditional probability is just equal to the probability of y smaller than z minus x. So this comes from x and y independent. Okay. So this conditional probability of z smaller than z is given by the probability of y smaller than z minus x. And then let's recall when the definition of the PDF of z is equal to the differentiation of the CDF of z over z, which is equal to the differentiation of the probability of z smaller than z over dz. But for now, we only have this conditional probability, which is not the same as this one. So to the left-hand side, that is first we consider this left-hand side, and we differentiate it over z. So similarly, from this form, we can see that this one is actually equal to the conditional PDF of z condition on x. By differentiating this conditional probability, we obtain the conditional PDF. Then let's look at the right-hand side here, this probability. And then we still do the differentiation over z. Here we do the differentiation over z. And we know that this probability is actually equal to the CDF of y at the value of z minus x, right? This just follows from the definition of the CDF of y. Over z, and then, as we have learned previously, this differentiation can be calculated as follows. We differentiate it over z minus x, and then we multiply it. Okay, so this is called the chain rule. You just need to memorize that you can do the differentiation in this way. And then, so for the first part, this is just equal to the PDF of y at z minus x. And for the second part, this is just 1. So we just don't put the 1 here, okay? So that by differentiating the right-hand side, we obtain the PDF of y at the value of z minus x. This gives us the equality f, the PDF of z given x is equal to the PDF of y at z minus x. So from this relationship, the probability relationship, we again obtain the PDF relationship. But since we want to obtain the PDF of z, then we can just use the multiplication rule. So the joint PDF of x and z is equal to the PDF of x times the conditional PDF of z given x. This is just the multiplication rule. So since we already have this equation here, we can replace this conditional PDF using the PDF of y. And then we obtain this product. These two terms are equal and they are obtained from this probability relationship. So for now, we obtain the joint PDF of x and z. So finally, to obtain the PDF of z, this PDF of z is equal to the integration of the joint PDF over dx. So when we integrating over all the possible values of x, we are just left with the PDF of z. So we can just plug in this product here. And we obtain this formula. So this one looks very similar to the convolution of the PMF between X and Y. This is the convolution for the continuous case. So this C here is also fixed, and we are just integrating over all the possible values of X. So that when C is the sum of two independent continuous random variable, the PDF of C can be calculated using this convolution formula. So let's give an example. So still a very simple example such that X and Y are uniformly distributed on 0 to 1. So let's consider the PDF of Z equal to X plus Y. Yeah, so we just rewrite the formula again. This is equal to the convolution of Fx and Fy. To solve this convolution, we have two methods. The first method is just use the property of this PDF of X and Y to calculate. So for the first method, these X and Y they all takes value on 0 to 1. So Z equal to X plus Y must belong to 0 to 2. Okay. Then we know that Fx is only greater than 0 when X is between 0 and 1. Minus Fy Z minus X is only greater than 0 when Z minus X is between 0 and 1. So these two are the PDF of X and Y, and they are uniformly distributed on 0 to 1. So they only have positive value when these two are in between 0 and 1. Okay? So this inequality gives us z minus 1 and upper bounded by z. So by combining these two cases together, so these two inequalities needs to hold at the same time. So let's combine them, and then we get x first must be greater than the maximum of 0 and z minus 1. So it must be greater than both 0 and z minus 1. So it's greater than the maximum between them. Okay? And then it must be smaller than the minimum of z and 1. Because it must be upper bounded by 1 and z at the same time. So it's smaller than the minimum between them. Okay. So now we define the range of x when both these two PDF are non-zero. So let's rewrite this again. This two product is equal to 1 if x is greater than the maximum between 0 and z minus 1 and smaller than the minimum of z and 1, and it's 0 otherwise. Now it's very clear. We already obtained the product of the PDF of this term. So we just need to do the integration. Of 0 and z minus 1 to mean of z and 1. And this PDF, product of PDF, is equal to 1. So by doing this calculation, we just obtain the formula maximum of 0 and z minus 1. This seems a bit unstraightforward. So let's write it in a more clear way. So recall that we know that z must be in between 0 and 2. First, let's consider when z is smaller than 0, then this term is equal to 0, because the maximum between z and 1 is the minimum between z and 1 is equal to 0, is equal to z, and then this maximum is equal to, wait for a while. The case Z does not belong to 0 and 2. Since you already know that Z is in between 0 and 2, so the PDF of Z is equal to 0. So the case when Z is greater than 0 and smaller than 1, then FZ is equal to Z minus 0, which is equal to Z. Okay. Z is greater than 1 and smaller than 2. Then FZ is equal to 1 minus Z. So if we plot the PDF of Z, where outside 0 to 2, the PDF is equal to 0. And then for Z in between 0 and 1, to Z in between 1 to 2, the PDF is 1 minus Z. So the convolution of two uniform independent random variables becomes like a triangle. In this method, we just simply calculate the product of PDF for different values of X, and then we do the convolution to obtain the PDF of Z. We need to pay attention that this product is non-zero when both the PDF is non-zero. So this two inequality needs to hold at the same time. And then we combine these two inequality, we obtain this interval of X such that the convolution is non-zero. This one minus Z. So we see from this formula, when Z is in between 1 and 2, then the minimum between Z and 1 is 1. Okay, and the maximum between 0 and Z minus 1, because Z minus 1 is greater than 0. So the maximum is 0. So the maximum is z minus 1. Oh, yeah. Sorry. Sorry, typo. It's 2 minus c. Yeah. Here, the figure is correct. The figure is 2 minus c. Oh, yeah. Yeah, but the curve looks like this. It's like a triangle. For this first method, we are just simply calculating this integration, and then we obtain the PDF of z. We have another way that we are not doing the calculation. We are just using the figures to obtain the PDF of z. We call it a graphical solution. Let's discuss 4 cases. First is when z is smaller than 0. The second is when z is in between 0 and 1. The third is z in between 1 and 2. And the last one is when z greater than 2. So let's plot the figure of the PDF of x and y. This is the PDF of x. Then 0 to 1, it's a uniformly distributed random variable. So here, first let's plot a figure of PDF of x. And then similarly, we plot a figure of PDF of y. Here we use the notation x instead of y because we want to make it consistent with the notation of the fx. But this notation doesn't matter. It's just a notation. Okay. So y is also uniformly distributed between 0 and 1. So now we have the figure of both the PDF of x and y. So first, let's do a transformation of the PDF of y. We want to obtain fy minus x. So it's like just flipping the PDF of y. This is -1. So by flipping fy minus x. Okay. So finally, we want to know the PDF of y z minus x, right? And then we first consider the case when z is smaller than 0. When z is smaller than 0, it means that we're moving it to the left. And this is -1 plus z. This is z. Okay. So it's just like we are moving this line to the left by a distance of z. And then we can see these two figures together. So when we multiplying fxx and fy z minus x, we can see that their product is equal to 0 for all x. Because when x is smaller than 0, the product is equal to 0. And when x is greater than 0, their product is still equal to 0. So let's plot a figure here. X multiplies by fy z minus x. Okay. This one is always 0. Let's consider the second case when z is between 0 and 1. So when z is in between 0 and 1, then it means then we can say that z, for example, z is here, -1 plus z, and z is here. Okay, so that becomes like this. Then we compare this with this. We can see that when z is smaller than 0, when x is smaller than 0, the product of fy z minus x and fx is still 0 because fx is 0. And when x is greater than z, since fy z minus x is 0, so the product of this and this is also 0. So the only region interval when the product is non-zero is for x in between 0 and z. Only this area is non-zero. This product to z, the product is 1. Here, to the convolution from -infinity to infinity. This is only equal to the integration from 0 to z. The product is equal to 1, so this is equal to z. Okay. For the third case, z is in between 1 and 2. Okay, so for example, like z, this is just 1. Okay, this is 2. So for example, say z is here. No, yeah. And -1 plus z is here. So it's like we are moving this line to the right, to here. Then we still compare with the PDF of x here. Oh, sorry. By comparing these two, you can see that for x smaller than -1 plus z, the product is 0. And for x greater than 1, the product is also 0. So the only region when the product is non-zero is in between -1 plus z to 1. So it's only non-zero in between -1 plus z to 1. So the product will be as shown in this figure. And then when we do the integration from -infinity to +infinity, this is equivalent to integrating from -1 plus z to 1. The product is 1. So this one is equal to 2 minus z. Okay. For the last case, z is greater than 2. So z is here, and this one is -1 plus z. This one is fy at z minus x. Now we move this line to the right a bit more. PDF of x, and then we compare them. So we can see that the product of them, the product of the fy of z minus x and fx of x is always 0 because they have no overlapping area. So that the product is always 0. Oh. So that the convolution, that is the integration, is always 0. summary. First, let's recap the case when z is smaller than 0. Their product is always 0. So their integration is always 0. That is the integration. Okay, so this is the first case. And then the second case, when z is in between 0 and 1, it means that we are moving this curve or this flip side line to right a bit more. Then the product of fx and fy z minus x is only non-zero from 0 to z. So the integration here is equal to z. And for the third case, when z is in between 1 to 2, derive the integration to be 2 minus z. And finally, for the case when z is greater than 2, we find that the integration is 0. So in summary, of z, which is equal to the convolution, is equal to 0 if z is smaller than 0, and is equal to z if z is in between 0 and 1. It's equal to 2 minus z if z is in between 1 and 2, and it's 0 again when z is greater than 2. So we can see that using the graphical methods, we obtain the same results in the method 1. Seems a bit complicated, but the main idea is to flip fy, and then we move it using this z here. Pardon, I can't hear. Oh, there's no middle. It's so you need to discuss different cases of z. So when z is smaller than 0, then it means that you are moving the line to the left. When z is greater than 0, it means that you are moving the line to the right. So for different values of z, you move the line to different distance. I suggest you can draw the picture by yourself and you can better understand it. So for example, like if z here is -1, then it means that you are moving this point to -2. So this will be from -2 to -1. But if z is like 1 plus 1, so it means that you are moving this point to 0 and this point to 1. So it means that you're moving this line from here to here. An easy way is to find the vertices. This is the 2 vertices of the line. So you find the location of these 2 points, and then you just connect them. So this is the easiest way. This may be a bit hard to understand, but I suggest you can give some fixed value to the z, like z is equal to -1 and z equal to +1. And then you can plot the figures and see how it moves. Basically, from these 2 methods, we can go to the same results. The graphical methods can help you better understand how the convolution works, like just convoluting the 2 PDF. So we're going to give one last example. In this example, we have very important results. So consider the sum of 2 independent normal random variables. So like x, for x, the PDF of x is equal to Gaussian distribution, that is the normal distribution. Okay. The variance is sigma x squared, and the mean is mu x. And for y, it's also a normal distribution where the variance is sigma y squared, and the mean is mu y. Okay. So if we want to know the PDF of z equal to x plus y, just use the same method, the convolution method. This calculation is a bit tedious and complicated. You can try it if you're interested, but now I'm just going to give you the results. So you can just memorize this results. So after the calculation, we obtained this formula. This one is exactly equal to the normal distribution, such that the mean is mu x plus mu y. is sigma square x squared plus sigma y squared. So we can see that the sum of two normal random variables still gives you a Gaussian random variables. And the mean of the z is just the sum of the means, and the variance is also the sum of the variances. So it is an important property when we have independent normal random variables and we sum them together. Okay, that's all for today. Thank you. Okay, sure.